how to find the nodal temperatures. In our case, we have 4 nodal temperatures to find, and we have our mathematical model, that is the boundary value problem. And so we'll go from the boundary value problem, that's differential equations plus boundary condition, to a system of algebraic equations in the nodal temperatures. So you're going from differential equations or differential equation to a system of algebraic equations. And you derive that system of algebraic equations using the piecewise polynomial approximation for temperature that we saw previously. And each equation will relate a nodal temperature to its neighbors. It's going to be a linear equation, and so for instance, if I write the equation at this node, it'll relate the temperature T2 to T1 and T3. It won't involve this temperature, for instance. And this becomes significant as you get more nodes, and so the equations will relate only the immediate neighbors. So we are going from calculus to linear algebra. And the system of algebraic equations can be written in matrix form, and usually you see this form written. T is a vector containing a nodal temperature. So in our case, T is going to be T1, T2, T3, T4. So that's what that's going to look like in our case. This is called the stiffness matrix. It comes from structural mechanics, which we will see later, and that's the force vector, and the boundary conditions will affect that. The heat generation term will affect that. Again, bad notation. That's not the heat generation term that we saw earlier. And then, so if we have a system of linear equations, we can solve that. That is a matrix inversion problem. So we'll invert that system of linear algebraic equations, and we'll get our nodal temperatures. Okay? That is our selected variables at selected points. And once we know the nodal temperatures, we can derive everything else from those 4 nodal temperatures through post-processing. So if I want to know temperature at any arbitrary point, right, if I want to know the temperature here, I can just use my interpolation to find that. So this I'll do by interpolation, and then I can differentiate my interpolation to get the heat flux, that is the heat flow per unit area. And then the crux of the problem reduces to how do we derive our system of algebraic equations such that it best satisfies our mathematical model. We can't satisfy a boundary value problem exactly, but we want to satisfy it the best we can. So we'll take a look at that next.